So on Friday of last week, we introduced different types of processes. Specifically, we talked about continuous processes, batch, and semi-batch. We also call the semi-batch transient. We talked about a few different examples, but as a reminder, let's take a moment, right, and we'll have maybe this section of the class. Everyone think of a few continuous processes, sort of the center chunk of the room. Think of different batch processes, and then this sort of slice over there, think of a semi-batch process. So take a minute and just come up with one or two that fit into that mold, and we'll run through them, and then we'll discuss if we agree or disagree if the ideas fall into continuous batch or semi-batch. Okay, so let's start off with the middle. Usually the easiest one is batch. What's an example of a batch process? Yeah.
Mac and cheese.
Mac and cheese. So that's a good one. Another batch process. So, yeah. Pressure cooker. Yes.
Biodiesel in your backyard.
Biodiesel in your backyard. Any individual step may be, but there's a lot of steps involved in that.
So you just dump it all in there and let it sit for a while.
I don't know. I guess I don't know the recipes very well, so it could be a batch process. Yeah, so a lot of cooking and household stuff that we do is batch is the most convenient, right? Because it's the simplest. You just throw all the stuff in there, wait a period of time, and then get it out again. Okay, so let's go over here, continuous processes. What ideas do we have for continuous processes?
Refining, oil refining.
Yes, that's a continuous process.
A boiler.
A boiler, continuous process. Bioreactor. Depending on how it's operated, I don't know if there's typically a lot of... Because for pharmaceuticals, a lot of drugs are developed in batch processes, like fermenters. Those would be a batch process. I'm not sure how many bioreactors are continuous. Your human body is a continuous process-ish. What else we got for continuous? Yeah?
Water treatment facility.
Water treatment, yes, that's a continuous process. Water comes in, water goes out. Otherwise, we're going to have a lot of accumulated water in there. Okay, very good. And let's look over here. Semi-batch. What's a good semi-batch example?
Crystallization.
Crystallization, yes. That's one we talked about in class.
Home water heater.
What was that?
A home water heater.
Home water heater. Yeah, I would say that's semi-batch. Yeah.
I just had a question. So do you have to have like some solid at the bottom for a semi-batch process?
No, not necessarily, no. You could have, a glass of water evaporating on a countertop. That's a semi-batch process, right? Because material is entering and leaving the system boundary as a function of time, and the total quantity of material in the system is changing as a function of time. So in reality, most everything that we're talking about, right, even the batch systems, a lot of household stuff, technically they really are semi-batch, right? Pressure cooker, if you have no steam being vented out of the top, then that would be a batch process, but in general, you're going to have a little bit of steam coming out, right? So semi-batch is kind of the real-world scenario, and these are more to approximations. Yeah?
So it's just a time where you have mass just leaving the system after you put mass into the system.
Yeah, so in a continuous process, a good way to think about this is that the mass is entering and leaving continuously at exactly the same rate. Nothing is changing as a function of time. In the batch process, nothing is entering or leaving as a function of time. You put everything in, you seal it, you wait, and then you take it all out. So anytime that something is entering or leaving and the total balance or the total amount in the system changes, that'll fall into a semi-batch process. And so a lot of instances, you may have some amount of material leaving the boundary, but it may be so small that you don't really care too much about it. Right, so semi-batch is in the real world the most common scenario probably, but for our purposes it's a bit harder to do the math on it, and so we leave that out to the end. So, these are the types of processes that we're going to see. Now in general, almost everything we're going to be talking about falls into a continuous process, because that is the way that we can optimize the efficiency of it, and it's the easiest one to perform calculations on. So in general, we are going to be assuming continuous and steady state. That are general assumptions, which basically mean that nothing is changing as a function of time. And to talk about that, I'm going to introduce now the general balance equation. So this equation is applicable for any conserved quantity, right? So this could be for mass is conserved, energy, momentum, and anything else that we could potentially think of. These are the ones that we care about most typically. So effectively what we're doing with this equation that I'll write on the board in a moment is we are being accountants, right? We're just making sure that we are not creating or losing energy or mass. Right, so we're just balancing the books, making sure that everything that comes in is being accounted for. And so we have input plus generation minus output minus consumption is equal to accumulation. So in the case of mass and energy, we can't generate or consume it. That would be a simplification that we would employ. But what this equation is telling us is that everything that we put into the system, right, and this is a general equation here for potentially, like let's say a chemical reaction, right? If I put a particular chemical into the system, I may be forming some of that chemical in the reactor. Some of it's going to be flowing out. Some of that may be consumed, and if there's a mismatch between how much is coming in and how much is coming out, there's going to be accumulation of that material in the system, right? But if we think of this like mass, right, we can't generate and consume mass in our processes, right? We're not dealing with any sort of a nuclear process, right? Mass comes in, mass comes out. We can't control what happens on the inside. So, if a mass balance, we have an input, we have an output, and any imbalance of that results in accumulation. If we have accumulation in a real chemical process, that basically means that the mass is increasing and increasing and increasing, which is more or less meaning your process is going to explode, right? So, what we're going to be doing now is taking this general balance equation and applying it to different systems. So, what we're going to say is that we have a population of a town. Now, here's the city limits of our town. We have people moving into the town. We have people moving out of the town. And we want to know is what is the rate of growth of the population. So moving into the city or town, let's say we have 50,000 people per year that move in. Moving out, let's say we have 19,000 people per year. We have people being born within the city, and for this problem we'll say 22,000 people, and deaths. It's a particularly bad year for this town, 75,000 people in the city. So the accumulation of people in this town, right, is the net rate of growth or rate of decrease. Right, so in this scenario, we have input, 50,000. Generation, 22,000. Output, 19,000. Consumption, 75,000. So the total accumulation in this case here, if you just add up all those numbers, right, you have positive, positive, negative, negative. We ended up saying that minus 22,000 people per year is the accumulation. So this town's population is decreasing. So if we were to apply this general balance equation to our most common scenario, a continuous process, what approximation do we make? What term always goes to zero? Yes. Accumulation. This is for a steady state process. So accumulation is zero in a steady state process, and that's the most common approximation that we are going to make. For mass and energy, generation and consumption go to zero because you cannot create energy, nor can you create mass in a chemical process. You can only work with the material that comes in or comes out of the system. So, this balance here can be applied in a couple of different ways. We have what they call the differential form. In the differential balance, this is just like the population example. This is where we look at the rates of change. Right? Differential is just like a differential in calculus. Right? We're looking at how does the rate of accumulation or input or output change. So what we're looking at is a quantity per unit time. Right? So we're looking at an amount per time. This could be amount of energy entering the system. This could be amount of mass entering the system. But it's at a certain rate of change. In this case here, we looked at it over the course of a year, right? That is the rate of change. But we could also do this as a function of days or seconds or time or whatever. The alternative is an integral form. And the integral form is we apply this balance over the period of a period of time, like a year. So you get to exactly the same answer, but it's two slightly different ways of thinking about the problem. Right? So for example, if we were to have taken the differential balance and integrated it over the course of a year, right? So let's call this P dot is the rate of change of population, dt. This part right here is the differential balance, right? The rate of change, right? Rather just the P dot, sorry. And the integral is the integral balance. And so if we look at the units, people per year times that by years, because you're integrating over it, the units work out. So another quick example is filling a swimming pool. So we're going to be filling up a swimming pool with, let's say, a garden hose at a constant flow rate, so very similar to the homework problem. So the volume in that pool is going to be increasing as a function of time. The slope of this line corresponds to the volumetric flow rate, so we can call this cubic feet per hour, for example. And this would correspond to the differential balance. What is the rate at which we are filling up this pool? Now the integral balance would say over some delta t time period, what is the total amount of volume that we have filled up into the pool. So in the differential balance, everything would simplify down to the V dot, which is some sort of a volume over unit time, is equal to the accumulation rate, the rate at which we are filling up the pool. If we think about this for an integral balance, the total volume that we have added is going to be equal to the total volume in the pool. So another way we can write this, you can say that the volume in the pool at some T1 minus the volume at some T0 is equal to the total amount that we've added into the pool. Right? This is an integral result here. Right? We're integrating the rate, which gives us a definite integral of T1 and T0 bounds. So these examples seem a bit trivial, but you'll find that sometimes it's best to think about things as a rate of change, and sometimes you'll have to think of them over a course of time. So in a continuous process, typically we're going to be using a differential balance. In a batch or a semi-batch process, we're typically going to be thinking about the material balance as occurring as an integral form. Any questions about that? It may seem just like semantics right now, but it'll all come to fruition soon enough. Okay, so what we're going to do now is start talking about balancing real processes and some tricks that we can use. The difficult part in this class is not going to be mathematics. The math that we are dealing with is much simpler than many of you have probably already seen for your experience, right? We expect a basic level of calculus, and towards the end of the class, we'll be starting to do a little bit of ordinary differential equations, but in general, the most difficult math that we'll be talking about is systems of linear or systems of nonlinear equations. So something that your calculator can easily solve, or you can solve in Excel in maybe 5-10 minutes. So the math is not the difficult part. The hard part is setting up the problem. Because in general, what we're going to be trying to describe is a chemical process with a paragraph of writing. And you have to translate that writing into a flow diagram of what's going in, what's going out, what's the composition, temperature, pressure of the stream in, composition, temperature, pressure of the stream going out. Once the problem is set up, the math and how we apply the equations is going to be relatively straightforward. But the hardest part is going to be setting up the problem. The easy part will actually be solving it. So the first step that we are going to undertake when we actually balance a process, and we'll go through an example of one we can balance later on, is to draw a flowchart So we're going to draw a flowchart and we're going to label our streams and the information that we know. So when we talk about a flow stream, we're going to be talking about a amount of material entering some process. In general, we're always going to draw our processes as big blocks. Our purpose right now is not to understand what's going on inside of the blocks, but to understand how much information we need to supply to this unit. Everything that happens inside of one of these processes is something that you'll be talking about next year in the junior level classes, right? If it's a heat exchanger, it's going to be relevant to your heat transfer class. If it's a chemical reactor, it'll be your reactor design class. If it's a distillation column, your separations class, right? So all of the actual mechanics of how the fluid moves, how heat is conducted, how reactions occur, all of that stuff is beyond the scope of the class. But what we're going to be learning right now is what's the total amount of energy that you need to put into that system. How do you balance the process and things like that. So when we talk about a flow stream, what we need to know is basically all of the properties associated with it. Temperature, pressure, composition, and total flow rate. And so for example, if we said we had air at 100 moles per hour, 320 degrees C, and 1.4 atmospheres. We have to communicate this information and draw it out on our process flow chart because the temperature and pressure that it leaves at may be slightly different. So acceptable ways to draw out a process flow chart are, you can say that we have 100 moles per hour flowing in. That's not quite specific enough. Then we need to say that 0.21 moles of O2 per mole of the air being fed into the system, or 0.79 moles of N2 per mole, right? This is the composition of the flow stream. Temperature equals 320 degrees Celsius, and pressure is equal to 1.4 atmospheres. Right? This is one possible way that we can communicate all that information. We need to know how much of each component is flowing into the system. So we can write that either as the total flow rate multiplied by the composition, or we can write this out as the flow rates of the individual components going in and out. So the alternative is we can write this as 21 moles of O2 per hour, 79 moles of N2 per hour, and the temperature and pressure. So both of those are acceptable ways to write it. Now the reason for this sort of rigor is because we may not know the conditions coming in or coming out, which means that we would have to come up with a nomenclature system for maybe this being unknown, or that quantity being unknown, or the total flow rate being unknown. And so we have to write out all of the information that we were given on the process flow chart, all the information that we are not given, then we have to subsequently fill in as an unknown variable that we are going to be solving for. So what we could write here is I wrote out the numbers, but if we didn't know, for example, total flow rate. So if we didn't know what the total flow rate is, you would say that n dot in is an unknown. In this case here, we know it's 100. But if we didn't, we would have to come up with a nomenclature system to say this. If we didn't know the concentration or composition, we would say that y of O2 is equal to 0.2, or sorry, y of O2 is unknown, and y of N2 would be 1 minus y of O2. So depending on the problem, you may not know the inlets or you may not know the outlets. But the key thing is, for every single property of a flow stream, whether it's the flow rate, the composition, the flow rate of an individual component, the temperature or the pressure, we need to have a nomenclature system ready and prepared in order to translate a word description of the process to actual mathematical terms that we can substitute and solve for. Okay. So a balanced process Our goal is to be when I refer to a balanced process, what this means is that all of the inlet and outlet streams, the composition and total flow rate is known for every inlet and outlet. So all in and out streams basically means I know exactly what and how much of each material enters and leaves through every single stream in the system. In the future, this will also include temperature and pressure. Right now, we're going to be focusing on mass balances, so we're not going to worry about the temperature and pressure too much, but when we talk about energy balances, this is going to be very important. This is going to be our goal here, is to eventually get to the point where we know everything that comes in and everything that comes out. So with that, let's do an example of a continuous process. Okay, so on a continuous process, let's write out our general balance equation. In minus out plus generation minus consumption is equal to accumulation. Let's simplify it. We have a continuous process. What term goes to zero? Accumulation, that goes away. Okay, now this is a mass balance we're going to perform. What else goes to zero? Generation goes to zero, and consumption goes to zero. So a continuous, open, steady state process has this balance. In is equal to out. No big deal. We can do a lot of damage with this equation. The example that we're going to go through right now is a very overly simplified example. The homework has some slightly more elaborate ones, but I promise things will pick up quite a bit. Right now we're going through the basics. So an example that we're going to go through right now is a cyclone separator. What is a cyclone separator? Anyone know?
Like a air separator?
Exactly, right? So a wood shop might have one of these for separating sawdust from the air. Why is that important in a wood shop? More than just a fire hazard, it's an explosion hazard. Sawdust is, can be explosive also. Okay. So in this particular problem, we have an airstream with 10% sawdust, and we are going to be separating that sawdust at steady state. And in this particular example, it's going to be 100% efficient separation, where we're going to have all of the sawdust going down and all of the air going up. It's going to be a perfect separator, which is going to be the uncommon scenario. So our first step is to draw out this process flow chart and figure out what we do and what we don't know. So I know from just prior experience that a cyclone separator typically would have one inlet stream, one stream flowing out the top, which is going to be the air, and one stream flowing out the bottom, which is going to be the sawdust. In time, you'll get better at drawing process flow charts that kind of make a more of an intuitive sense in terms of what's going on. So I'm going to say that we have 100 kilograms per hour coming into the system, and that this is 10% sawdust. So I would write that as 0.1 kilograms of sawdust per kilogram of the feed coming in. Right, that's 10 weight percent. So in the problem statement, it may say something along the lines of, this is a 100% efficient separation, so no sawdust goes out the top and no air goes out the bottom. So how we would mathematically write this is, first it would be convenient to label the streams. Now I label them 1, 2, 3. You could label them feed, top, and bottom. Right? There's lots of different ways that you could think about labeling the system, but coming up with a clear, consistent nomenclature is going to be critical to solving more and more complex equations. So our goal, right, is we need to know the inlet and outlet streams for every single stream and every single component. So at the top, we need to solve for what is the mass flow rate of stream 2 for air and the mass flow rate of stream 2 for the sawdust. And coming out of the bottom, we're going to need to know what the mass flow rate of the air is and the mass flow rate of the sawdust. So in my nomenclature, and this is typically how I like to do things, M signifying the mass flow rate, dot rate of change, 3 corresponding to stream 3, air corresponding to the flow rate of air in stream 3. Same thing for the sawdust, and same thing up here. So to simplify things, if we say that this is a 100% efficient separation, what we need to do is simplify our equations here. If we're saying that there's no sawdust coming out of the top, then we know that m dot 2 saw is equal to 0. Coming out of the bottom, we have no air, m dot 3 air is equal to 0. So we essentially just need to solve for these two unknown quantities. Once we know these two unknown quantities, we know the total flow rate in and out of the system for every single stream. Now I'm sure almost everyone can do this equation in their head, but we're going to go through the example just to highlight how it's done. You will have more complex problems in the homework. So what I want to highlight here is the strategy, the methodical strategy to go through and solve these problems. Okay. We are trying to apply our general balance equation. In equals out. Now we can apply that in actually 3 different ways. There's no reaction going on here. So everything that comes in comes out exactly the same way. We can apply this balance equation on the total process. What is the total mass in, and how does it relate to the total mass out? We can apply this to air. The total amount of air in has to be equal to the total amount of air out. And to sawdust. The total amount of sawdust in is equal to the total amount of sawdust out. Now in general, it's not going to be clear which is the right balance to start with. So we're going to practice on all of the different balances. Because when I write this equation here, the only way that I can solve this equation is by having it reduced down to one equation and one unknown. Many of the balances that you'll be looking at on the homework problems and future problems in the class, you'll write out a balance. Maybe you'll have 2, 3, 4 unknowns. Right? So you may have to write down 5 or 6 different balances before you find the right one that you can actually solve, and then you can move on to the next, and move on to the next, and move on to the next. This one here is exceptionally trivial of an example, but it's just sort of a warm-up. So we're going to start off doing a balance on sawdust. So oftentimes, if you look at my solutions, you'll see I write in equals out, just a little reminder of what our material balance is for the sawdust. So what we have to keep track of here is how much sawdust is coming into the system and how much sawdust is coming out of the system. So we can write this as 100 kilograms per hour is being fed into the system for every 0.1, you have 0.1 kilograms of the sawdust per 1 kilogram of the feed. Right? So our balance on sawdust, the units have simplified to kilograms of sawdust per hour entry. This is a differential sawdust balance. This is all the material that is coming into the system. Coming out of the system, we potentially have some mass flow rate of sawdust for stream 2. We already have said that that approximation is 0. And coming out of the system, we have material coming out of the bottom, which is m dot 3 for the sawdust. In this example here, we have one equation, one unknown. And we can very trivially say that m dot 3 saw is equal to 10 kilograms of dust per hour. We are effectively halfway to balancing our process. When the problems get more complicated, breaking it down into individual steps, writing it out, translating what we do and don't know into unique specific variables, that is going to be the lifesaver of the class. Okay, let's apply the same thing but for air. Balance on air. Again, this is in equals out. So the equation I would write was 100 kilograms per hour being fed to the system times 1 minus 0.1 kilograms of air per kilogram of feed. This is equal to what's coming out of the process, which is going to be m dot 2 air plus m dot 3 air. And we already said that this is 0. And we find that m dot 2 air is equal to 90 kilograms per hour. No big deal, right? The last thing that we'll do is a total balance. Everyone can see this part of the board? Is that good? Okay. All right, so we have a total balance, which is the total amount in and the total amount out. This is going to be 100 kilograms per hour coming into the system. Coming out, we have the air out of the top and the sawdust out of the bottom. 10 kilograms per hour plus 90 kilograms per hour. And it works. We are okay. So what we've just demonstrated here is the application of either a species balance, right? Sawdust is one of the individual species in the system. We did that for sawdust, we did it for air, and we did a total balance. In this case here, it didn't matter where we started. The problem was so easy that we basically could have figured it out in our heads. But when things get a bit more difficult, you may find yourself in a scenario where you write out one species balance, two unknowns. You write out another species balance, two unknowns. You write out the total balance, 2 unknowns. Right? So you may find yourself in a scenario where you have multiple equations with multiple unknowns that you can't solve in this really simple, straightforward manner. But the strategy that you will be using throughout the entire class, whether it's mass balances, energy balances, thermodynamics, whatever the case is, this is going to be the starting point. Drawing an accurate process flow chart, labeling each of the individual streams. Sometimes numbers make sense, sometimes words make sense. Labeling each of the unknowns that we have. Flow rate of the individual species for which stream. Right? Because if, let's say I have a 3-component system with 3 inlet and outlet streams. That's a total of 9 variables that I have to solve for. Now, if you name them M1 through M9, that's going to be really confusing. Right? It's much better to have, mass of A1, mass of B1, mass of C1, right? For components A, B, and C. The more diligent that you are, and the clearer that you set this up, the easier it is going to be to go through and actually balance the problems themselves. The balance is in equals out for probably 99% of the stuff that we'll be working on in the class. Well, for the first stages. When we talk about reactions, we'll have generation and accumulation there. But in general, in equals out is going to be what we're working on. So the goal then is you take all the information that you've put into your process flow chart, and then get an algebraic expression using your general balance equation, and then solve for your unknowns. This is the general procedure that we're going to be working on, but again, this is a fairly trivial example. So one other really important concept to this here is what they call coming up with a basis. Now, the basis for this problem that we solved for was 100 kilograms per hour feed. Now, what are the odds that we're going to have an actual process with just nice, beautiful, pretty numbers like 100 or 1 or something like that? In general, rarely. So the basis it's the condition used to solve the problem. In general, you guys get to choose the basis, and you can change the basis, and nothing changes at all. So in general, you can set the total amount in or out for almost any problem that we're going to be working on in the class. Right? Because I could have very easily rewritten this problem here, and instead of saying 100 kilograms per hour of contaminated air is fed to the cyclone separator, I could have said some amount of air is fed to the separator. And that air is 10% sawdust. 100% of the sawdust goes out the bottom, and 100% of the air goes out of the top. Now, this problem solution would have been exactly the same. But instead of me asking, what is the flow rate of sawdust out, or what is the flow rate of air out, I could have said, what fraction of the feed goes to the top stream, what fraction of the feed goes to the bottom stream. So you could have solved this problem for 100 kilograms per hour, you could have solved it for 100 kilograms a second, you could have solved it for whatever you wanted to. And it wouldn't change the ultimate goal that you're trying to figure out what's the ratio of these individual streams. Now that idea is the idea behind what they call scaling the basis. So when you scale the basis, we would then multiply each stream by whatever the basis is. So in general here, I want to solve these problems with nice, easy numbers. Right? But let's say in the real process, it's not actually 100 kilograms per hour being fed to the system. It's, let's say, 246. So all I would need to do to convert these answers to the real process is times everything by 246 divided by 100. New basis, old basis. Apply that for this one here. 246 divided by 100. New basis, old basis. Not the super rigorous way right now of communicating this, but in general, the idea of scaling a basis will become quite trivial. So basically, what I'm saying here is that to get the new flow rate for any particular stream, you times the old flow rate times by the new basis divided by the old basis. And you apply that for every single flow rate in the process. Same idea could be made, for example, if I say I want a 50-50 mixture of sulfuric acid and water, right? You would solve that for maybe adding half a gram of sulfuric acid, half a gram of water. But then let's say you need 17 gallons of it. Well, then just times everything by that new basis, for example. I did mass to volume, but you get the idea on that one. So in general, solve the problems in an easy to use set of units. And then once you've balanced the entire process, you can scale every stream in and every stream out by the same amount, following this general equation here, right? You've chosen a basis that is easy to solve the problem, in this case here, 100 kilograms per hour, and then we scale it to whatever the real conditions are that the actual process goes through, and that's called choosing a basis and scaling a basis. Okay, any questions on this? So the homework has some material balances, and what they're asking for is this drawing with streams labeled and variables for everything that we don't know. Then you'll be applying species balances and total balances to solve for the unknowns, right? So I will have office hours tomorrow. There's office hours today. So please come talk to us if you have any questions about balancing those problems in the homework. Okay. See you on Friday. Oh, I believe there's also a quiz on Friday too, so don't forget about that.